Hi everyone. In this video, I'll introduce L'Hopital's rule, which is a method for finding the value of certain indeterminate limits. L'Hopital's rule makes the following assertion. Let's suppose we want to take the limit of a fraction, which I've called f of x over g of x, and let's suppose this limit turns out to be an indeterminate form of the type 0 over 0 or infinity over infinity. It turns out in this situation, we can take the derivative of the numerator and denominator without changing the value of the limit. So the limit of f over g is equal to the limit of f prime over g prime. And that's helpful because things generally get simpler after taking a derivative. But this equality is only valid if it's possible to actually find a value for the limit of f prime over g prime. But if that limit does exist, or even if it evaluates to positive or negative infinity, then it's equivalent to the limit of f over g. Importantly, notice this is stated as the limit of f prime over g prime, which means the derivative of the numerator and denominator are being taken separately, which is different from differentiating the fraction as a whole, which would require the quotient rule. But because it's f prime over g prime, that means that the quotient rule is actually not needed when taking these derivatives. Let's see if we can calculate this limit, for example. Before we resort to any fancy methods like L'Hopital's rule, we should check whether those methods are suitable or even needed in the first place. So as a first step, let's try just computing the limit in the usual way and see what happens. To show the effect of x going to infinity, I've used this notation that gives the impression of infinity being plugged in as though it were an actual number. And it should be understood this is just a matter of convenience. Infinity, of course, is not really a number, but writing the limit like this could just help us make sense of what's going on in the numerator and denominator. In the denominator, we're cubing a number which is approaching infinity, which is just going to make it approach infinity even faster. Likewise, in the numerator, when I take 2 times a number which is going to infinity, that's still going to approach infinity, just a little bit faster. Now, how do we interpret this e to the infinity? Well, that would also be approaching infinity. That's because e to the infinity represents e, which is about 2.7, getting multiplied by itself over and over again. And the more times we multiply 2.7 by itself, the larger the result is going to be, taking us closer and closer to infinity. Another way to think about that is using the graph of e to the x. We can see that when x goes to infinity, the y values on this curve are also going to infinity, which gives us further reassurance that our interpretation of e to the infinity is correct. Also, subtracting 1 isn't going to prevent a quantity from approaching infinity, and so what we're left with is infinity over infinity, a result which we know is indeterminate. That just means we need more information before we can find the value of this limit. Fortunately, we know a result of infinity over infinity gives us permission to use L'Hopital's rule. So let's try it. To set myself up for using this rule, I like to put a capital H above the equal sign in my next step, and this just indicates to the reader that L'Hopital's rule is being applied here, and that the limit we want is equal to whatever follows from here, at least provided that a value can actually be found. Now, L'Hopital's rule tells us to take the derivative of the numerator and denominator. The denominator is x cubed, so the derivative is 3x squared. For the numerator, we use the chain rule to get a derivative of 2e to the 2x. Pause and convince yourself if necessary. This new limit is certainly simpler than the one that we started with, but you can check that this still provides a result of infinity over infinity. So you might think this was a waste of time, but this result actually gives us permission to use L'Hopital's rule again to get an even simpler limit, because we still have infinity over infinity, so L'Hopital's rule is still applicable. So I put a capital H to indicate another use of this method. And now we take the derivative of numerator and denominator again. Our denominator is currently 3x squared, and the derivative of that is 6x. For the numerator, we can use the chain rule again to get a derivative of 4e to the 2x. If we try to evaluate the limit now, we still get infinity over infinity, but this allows us to use L'Hopital's rule a third time, and this seems to be going somewhere since we're getting simpler results each time. So take the derivative of the numerator and denominator one more time, pausing to check these results if you need. And check that now the limit evaluates to infinity over 6. At this stage, we need to stop taking derivatives. We don't have permission to use L'Hopital's rule anymore because the rule as stated requires 0 over 0 or infinity over infinity. It's not applicable to infinity over 6. On the other hand, we don't need it to be applicable because we can see the answer at this point. When a quantity which is approaching infinity gets divided by 6, it's still going to approach infinity, just at a slower rate. And so infinity is the answer to the limit that we were originally asked to calculate. As a quick check, it wouldn't hurt to pause the video here and graph the function we were given just to make sure this result actually makes sense. Now let's try this example. Before doing anything fancy, you should always check if the limit can be evaluated with basic methods first. In this case, we start by just checking what happens when we input numbers which are slightly larger than 1, because x is approaching 1 from the right after all. So pause and convince yourself that the denominator of both terms will be slightly larger than 0 in this case, which is going to cause both the terms to approach infinity. So we see this result as infinity minus infinity. If you're tempted to cancel infinities, don't ever do that. It's possible that one of these infinities is larger than the other, and in general, we should never treat infinity as though it were an actual number. What you should do at this stage is recognize this result as indeterminate. It is in that list of indeterminate forms that I gave in the previous video, and that just means we need more information to solve this problem. Unfortunately, we don't have permission to use L'Hopital's rule since that requires us to have a single fraction of the form 0 over 0 or infinity over infinity. Here we have infinity minus infinity. But if what we want is a single fraction, we could always get one by forming a common denominator. So let's see where that takes us. The common denominator would be ln x times x minus 1, giving us this result, which you can pause and check if necessary. And now let's see what happens if we try to evaluate this limit one more time. You can pause again and check that this provides a result now of 0 over 0. And this does give us permission to use L'Hopital's rule. It was just necessary to form the common denominator first. So we'll set this up just like before, using a capital H to indicate my use of this method. Now take the derivative of the numerator, which in this case is 3 minus 2 over x. Then we use the product rule to get the derivative of the denominator. After that, try to evaluate the limit again by letting x approach 1, from the right, technically. You can check that the numerator simplifies to a value of 1, and that both terms in the denominator simplify to a value of 0. And so we get this result of 1 over 0, which does not give us permission to use L'Hopital's rule again, but that's fine because we know this will result in either infinity or negative infinity, since we get large results when we divide by numbers which are close to 0. We do need to check whether we're dividing by a positive or negative number close to 0, since that will tell us which of these two possible answers is correct. For that, we make use of the fact that this is a one-sided limit. We know that x is actually a little bit larger than 1, and so in my first term, I see 1 is being subtracted from a number larger than 1, giving a positive result. And we also know that the result is positive anytime we take the log of a number which is bigger than 1. To convince yourself of that, you can remind yourself of what the graph of ln x looks like. From that, we know the numerator and denominator both represent positive numbers, meaning that when we divide them, the result must be positive infinity. And with that, we've successfully answered this question. Here's another example, which I'll suggest you pause here and try for yourself. And when you're ready to look at the answer, let's continue. Your first step should always be directly trying to evaluate the limit, which could look as you see here. Let's examine this e to the infinity. We saw before that this could be interpreted as infinity, and the reason for that was because when we look at the graph of e to the x, we can see that the y value is going to infinity when x goes to infinity. To figure out the behavior of the e to the minus infinity, we can make a similar consideration. Just check the behavior of the y value when x goes to negative infinity. In this case, we can see that y is getting closer to 0, so that's the value we put in for e to the minus infinity. So with a bit of cleanup, we get ln infinity minus ln infinity. Again, avoid the temptation to cancel these, since infinity is not a number and these might actually represent different values being subtracted. To interpret ln infinity, we can look at the graph of ln x. We can see that as x goes to infinity, y is also going to infinity. And so once again, this provides us with the indeterminate form infinity minus infinity. It would be better if this were 0 over 0 or infinity over infinity, since that would give us permission to use L'Hopital's rule. So just like the previous example, we should be thinking about ways to combine our two terms into a single fraction. In this case, we can do that using the log subtraction rule. When we apply that rule, we do end up with a log of the fraction that you see here. And when you evaluate the limit of that fraction, you do get infinity over infinity, but it does remain inside that logarithm, so you might wonder if that prevents us from using L'Hopital's rule. Fortunately, this is a problem that's easily fixed. It turns out we're allowed to pull the limit operator inside of our logarithm, as you see here. In general, you can always pull the limit inside a continuous function like this, and since logarithms are continuous, it's fine to do this. We just saw that this inside part provides a result of infinity over infinity, which gives us permission to apply L'Hopital's rules there. So let's set ourselves up to apply that rule. And we come up with this result after taking our derivatives. Pause and check if necessary, and don't forget to use the chain rule in the denominator. You can also check that if we try to evaluate this limit again, we now end up with the ln of 1 over infinity. We know that when we divide by a huge positive value, the result will be a small positive value, which is close to 0. So now, what happens when we take the log of small positive values? Here again, it would be useful to remember what the graph of ln x actually looks like. We can see that when the x values approach 0 from the right, the corresponding y values are going down to negative infinity. And so, negative infinity is how we interpret this logarithm, and this provides the answer to this question. From the last couple of examples, we saw that if you're faced with a type of indeterminate limit that doesn't grant permission for L'Hopital's rule, you might be able to fix that problem by just doing a bit of algebra first. For infinity minus infinity, like we saw in the last two examples, the key is often to form a single fraction either by forming a common denominator or by using laws of logarithms. Other types of indeterminate forms would require different strategies, and we'll look at that in the next couple of videos. But for now, this is all I have, so I'll see you next time.